Okay, we start talking about like attention model, but before that, like I like to talk about the Word2Vec model first. So um, basically, if you remember, like last time we talked about RNN, uh, it's most one very important application of RNN is doing um, natural language processing. And to start with, like we always have like maybe some words, like maybe just make up a arbitrary sentence like this is a bat here. And so we'll first say have the word like convert into some vector, and then the vector we can be plugged into our neural network models. So all these vector will have the same name. So let's say a typical name will be like maybe 1024, something like. And this will be like this conversion here is like a very popular model to do that is along with the Word2Vec model. Um, and we will kind of like give a little bit time to talk about that. And of course, you may extend this idea to like an other domain as well. For example, like you may try to do uh, what I want to say, if you have some audios like coming in, or like if you have some music coming in, maybe you can get a kind of like period of like signal and convert to a particular representation like using similar. But yeah, say like let's think of like natural language processing here. I say the application is most obvious. So say now we're trying to do this conversion into a vector representation. So to start with, like uh we will just I will use something called a P-Word2Vec model. This P-Word2Vec model is very intuitive. So think of like we're trying to model the conditional probability of a word, like a center word with a surrounding word. So let's say if I have center word, like let's just take this as a sentence here, like a word, a bad italic. Maybe this is a center word. I call it like WC here, or like in this case WT here. And then a surrounding word, sometimes we will denote WO here, like this word here. So we're trying to um, estimate this joint probability, like this like PWO given PWC here. And what I want to what we want to do is that based on all the training tests we have, like maybe the entire all the word, all the documents on Wikipedia and so on, we want to maximize a joint probability, or like not the joint probability, the product of conditional probability of the surrounding word given a center word. We've given some windows here. Like let's say this window M here, I can take M equal to 2, then I will be like for forever, whatever the center word will consider like 2 words before that and 2 words after that. And we want to find the model probability distribution here. So for different theta, right, we have like different conditional probability here. We want to maximize this theta such that like given our training data here, um, this product conditional probability and will be maximized. So here, of course, I will also like not consider only this center word, right? We will move around this center word to next center word. We have different windows. Then we also try to take that into account. So therefore, we report that like all the tasks or all the work like in the training document as well. So then okay, maximize this thing. So maximizing this thing, of course, is the same as minimizing the minus log probability of this one here. So because in machine learning, people usually like to do minimization rather than maximization by the convention. So let's say we take minimize the log of this instead. So then we will have this one instead, right? So and so from that, like we'll get the theta, right? So if we try to minimize that, okay, eventually we get the theta. What are the theta really? the filters will be essentially, um, or actually, in this case, we didn't really specify the filter, but we'll assume the model will be like this. So if I have a center word and an outside word, I will assume the probability will be just equal to something like uh, the inner product of like UO and VC, and then we normalize with with softmax. So then like after like we solve that, like we will have like the theta is essentially all the U and V here, right? In the sense like it will be um the theta will essentially be like for all the words like in the dictionary, we have one U and one V for each of the word. So for example, I will have a UA, VA, or UN, VN, or U is, V is, and also why are we repeating this U here? VA and VN and U is, V is, and so on. And all this will be the features basically. And after you solving that, then this will be your representation basically. You can take this as your representation, U and V. Typically, like what we can do also is like uh, we will just simply use one representation. So instead of like take U and V as two separate representation, we can just like for example for the representation vector for UA will be for A will be just like UA plus VA and take the FH of that. So is that clear? Oops, I guess it's my, oh, okay. Hmm. Now let's go a little bit in more detail. Let's see the update here because I think it's interesting to talk about the updates here. So if we just mentioned that like we have the loss function now is something like this. Let me just use a find a pen here. Maybe something like this. So 1 over t, sum over t here. T is like 1 to t here for all the word in the document or in the training documents. And then we look for the surrounding words like j, index like with a window like from minus m to m. So the window size is 2m. And we have j is not equal to 0, excluding the center word here. So we want to uh, minimize this thing here. P W T plus J given W, the center word is T with theta here. So let's say I'm also like again we mentioned that like this P theta or like let me just write P, the outside word given the center word is defined as just the softmax of like U outside word transpose times V center word here. And so therefore it will be equal to UO transpose VC and exponential it's the same thing here, right? But okay, by the way, like I let me ask you a question here. So I should softmax is essentially trying to normalize uh this UO transpose VC here because in general like UO transpose VC won't be okay. I'm sorry, like I probably need to put an exponential here also because I want to make sure this is positive. So exponential UO transpose VC won't if I consider all the possible value here, so it won't normalize to one in the sense that this probability is not won't be really a probability because it won't sum over to one here. Um, so yeah, okay. Anyway, like probably like I won't ask you this one here. So what I want to say, like, I want to normalize, um, make sure that like when I have like for all the possibles out, or like if I sum over all here, this should be sum over one, right? So therefore, like I should consider like for all the O, maybe I call it O pi here, U O pi transpose we see here, O pi here. So I should have like this normalized by this like sum over O pi mu uh, exponential U O pi transpose in VC. So that I can make sure that like I sum over this over O, I should get one. So now uh, let's say let's give a more precise example. Like let's say we earlier have like a sentence like this is a bat, something like that. And let's say I have this is the center word, this is the center word here, and O is an outside word here. Let's say M is equal to one. I just look up one ahead and sorry, one before and one ahead of the center word. So I now to minimize that, like we can simply okay think of like if I have this is my loss function and know that like for example this is like all the words in the dictionary here. So my filter then will be something like U this, V this, U is, V is like U A, V A, and U bad, V bad, let's say. Now, so for this loss here, I of course I can be just doing steepest descent, so I just take if I have like some initial filter there, my update filter will be like just filter minus a epsilon multiply the gradient of this loss here, right? Gradient of this loss here. And if let's say like be more precisely, let's say like actually that's one remark here is like if I have here like typically I have this really kind of like dumbed down case here. I only have like 4 words in the dictionary, but in practice, like for example, English language, it's easily have like maybe 100,000s of like words there. Then this update here will be very kind of like expensive, right? This gradient update because your filter is a very high dimension actually. You need to take the partial derivative with respect to all these 100K variables here. And for many of that like you see like here of course I if I consider like just a particular what I want to say, let's focus on a particular T here. Let's say like as you say scan through for example you have what I mean is like when you have a document here or like a long piece of like document for training here. So you have a center word somehow sentence one. Let's say I have like supposedly there's also the sentence that this is a bat here again, and there's more words like in the document here. Maybe there's a word that here, like was here, like some other words here. So again, if I have a center words here, if I just consider this center words here, so that basically correspond to like a particular T here, like a particular center word here. And I look at the loss, that's just a particular loss. If I'm seeing that there's a word like before that, so I'm also like in what I mean is I just look at a particular J here. So I will, or actually let's not just look at a particular J, but look at the entire window. Let's say for this target word here, I look at the window like 2n+1 window here, like one m word before that, m word afterward. And so based on this piece of information, now I want to update my filter here. So then again, I can just compute the stupid design here, but I just take one t here, right? So I don't have this summation here. Now I just look at one particular t here. The thing is, like, if you look at this probability here, because the probability is modeled by this softmax, the numerator here, of course, will only depends on the outside word and the center word here, the UO and VC here. But what's below here will depends on all the U of all the words, basically U of all the words here. So that's what I mean. Like if you look at just this particular phrase here and you want to update the filter, you should update not just the filter of like the uh, the V is MU this here. Apparently V is MU this will be in your loss here, in this like loss what means in this loss L here. But also like it will also this L will depends on like, for example, like you that and you was. So you ideally you should update this like you that and you was and like all this other like you have like 1000K of like depends on like the size of the dictionary. So this is something is not desirable, and that's why like eventually like people don't actually implement that this way. But okay, let's assume like we're going to implement that way. But and also like let's look at just how U and V will be updated, because I think that will give some insight as well. This is kind of interesting. So again, like I have the loss here is this one. Okay, I have a target word. Like let's say I have the target word like uh again I call it like just center word. Let's say like I have the target center word like C here, and I have some outside word there, and the probability is given by softmax of this guy here. And let's look at the gradient of this loss here, like for this L here. So if I take the gradient, or like take the partial derivative with respect to let's erase this one here. Just with respect to like log, let's look at just like one of these guy here, like instead of like the entire thing. Like so, just look at like log P O given C, let's say, minus log P O given C here for one outside word and for center word, and this will be equal to basically minus UO transpose VC, and then minus a plus log summation O pi exponential U transpose O pi VC, right? And then let's say let's just take the derivative of this one with respect to VC here. So just minus log PO given C with respect to VC here. So we have to take with respect to VC, will just give us UO, give us just UO, right? Minus UO. And for this guy here, will be something like I need to first like log something. I will like take the inverse of this guy. So inverse like exponential UO pi VC, and then take the derivative of this with respect to VC. I will have like a sum of like exponential UO pi transpose VC O pi and UO pi, something like that, right? And so what's interesting is if you look at this guy here, this one I can, okay, this is a O pi is actually a different dummy variable. Let me maybe put this X here. Put this X here. So this one here is actually I can push this. This is a just a constant. I can push it inside here, and then this one. What I want to say is that maybe I just do it this way. Here. So if I move it to here, then this one here is nothing but really this one again, right? It's just equal to P x given C, right? So therefore, like this expression is actually minus UO plus XP x given C UX. Now, if I think of like, if I use this to kind of update VC here, so I should have an update like staples design update will be like VC will become like VC minus epsilon of this partial derivative, right? That will be equal to plus epsilon UO minus epsilon x px given C UX. So what's interesting is like there's some nice physical interpretation here. So just based on like our observation that like I have an outside world is like, let's say my outside world could occur with my center word here. I should update my center representation such that like VC is more similar to the outside representation there. It's VC is more like UO here. But at the same time, like I try to make VC less similar to the average of all the U's there. So for the rest of the U, so given my center word of there, so I can find the conditional average of the U's there, and I want to make VC to be less similar to this average. So get farther away from this average, but it's get closer to UO. So it makes lots of sense basically. And I can repeat that, like, but I'm not going to repeat this. So I can take the partial derivative of like log PO given C with respect to like UO also. And you will find that like this will be equal to minus VC 1 minus PO given C. And then again, if I use a steepest descent update, then I should update VO as UO as UO plus epsilon VC 1 minus PO given C. So again, like this is interesting. So what is saying that like if I have for a center word like C here, if I find that an outside word is O here, I should make my UO representation more like the center representation of the VC there, but it's also like scaled by that this like 1 minus PO given C. So meaning that like if my outside representation, if my O, PO given C is already very close to 1, that means that like if I have the center word is equal to C, the probability that get outside word is equal to O is already very likely, then I won't kind of like make UO to be very much like similar to VC, uh, as much as like if I have like the probability of O um, given C is smaller. So if probability of O given C is like small, is close to 0, then I will make like UO like more similar to VC. So okay. So this is like somehow like of this P Word2Vec. Uh, I would say like kind of representation. So as I mentioned, like this. Okay, okay, yeah. So the problem for the P Word2Vec is like you see like when I do the update here, I only consider update of VC MUO here. But if I look at the loss here, like if I consider the loss is essentially sum of this log PO given C, right? If I just look at a piece of the loss at PO given C here, actually you all the use here will depend on this loss here, right? So therefore, supposedly I should update all the use as well. So therefore, like people don't actually use this model. They kind of simplify the model a little bit. So instead of like using sigmoid to kind of normalize the probability, or not sigmoid, to use the softmax to normalize the probability. So they use sigmoid instead. So they will just say, okay, I have this. You can think of this again like some kind of score, co-occurrence score. Like if this inner product is high, it's likely to have co-occurrence. Then I will kind of not exactly normalize that, but like uh, use a sigmoid to kind of like uh, compress that magnitude to the range of 0 to 1. And then I will take this as a probability kind of, right? But note that the problem is that this probability it doesn't care about, this only care about the positive part. As you can see, like when we're using like the real Word2Vec, this supposedly like a more accurate model, you should consider both the negative and positive. You should get like closer. For example, like if you have the VC here, you should get closer to the actual, I mean, you should have VC closer to the UO, but at the same time, you want to make VC to be farther away from like all the rest of the U's there. So therefore, like they also introduce like another terms here. So it's exactly borrowing the same idea like as the more accurate P Word2Vec model. So we will try to make sure that like um we want that like U and V to have a high co-occurrence. Like if they actually co-occurrence, like I want this probability to be or like this value to be big. Uh, but at the same time, like we want to make sure that like when I arbitrarily sample like some other like irrelevant uh, words there, so this uj here should be far away from VC. So I can make sure that uj is far away from VC. Then what does that mean is that this probability. So because I consider this now is like some kind of probability, so I want to make sure that 1 minus this probability is big. So therefore, we have the overall model will be like this. Like we have this loss function is like this one instead, trying to maximize this, but I'm also maximize this guy. And then we're trying to like minimize the negative of this thing here. So a final remark here is I should samples every time when we update, like basically when if you doing training, what's going on is like you have a long piece of document here. So you have T like moving around here, or like maybe I call it C here, it's moving around here. So I have like consider this is the center word, and then I'll look at the windows, kind of around the center word here. Let's say I look at representation here. If this is the UO here, now I should update my UO and VC and something based on like trying to minimize this loss here. And of course, like this also like will depends on some other words here, right? So I have some other words here will be uh, sample like uh, from this distribution PW here, and this PW can be just a, of course, a naively you can just use the word distribution as just the unit frequency distribution like for all the words. Like for example, like you can just build a kind of a distribution like what's the occurrence like probably, so what's the occurrence of like, and like what's the occurrence of phases and so on, and then you normalize that into a distribution. Um, but usually we will modify that a little bit. For example, like let's say you build a statistical distribution of all the words like as U W there. Then for PW, you will take like kind of like proportional to let's say 3/4 of UW instead. This is trying to de-emphasize some of these very frequent words. For example, we have the polans and like maybe and off is like super common. So we want to de-emphasize that. We want to not always like pulling kind of words like from these like very frequent word. Instead, sometimes we kind of pull from the less frequent word. So okay, this is the word-to-word model. Um, so also like to mention uh, something like actually uh, like P word-to-word model. Word-to-word is around like 2014, I guess, something like. And before the people have also like try to kind of general have like create some word representation even before that. So that's a very seminal field that you look at known as topic models or latent semantic analysis. That is like before like deep learning is it was a thing, and so what they did there like is actually you can think of like performance wise it sounds seems to make more sense. So what they did is like, okay, why we need to really like go through the entire document or like entire all the documents in the entire database and scan for like one word at a time and go backward and forward. It looks like pretty expensive to do. Like because every training you need to redo this like every time. It looks like very expensive. Why don't we just have like all the document and then we summarize with the co-occurrence like statistics? Let's say we just say, okay, how many times we have like A and window will co-occur at the same time. Say let's say A windows will be co-occur maybe like with a probability of 0.001, let's say, and maybe you have like two words again like goes and flew here with a co-occurrence of like 0.01, let's say. So why don't we just generate a kind of like a joint distribution of co-occurrence to form some kind of like huge matrix and use that to train a representation instead. So then like uh, you don't need to every time to just like go through all the documents in the database and to compute like almost like the same kind of like statistics as like it would be like embedded by this co-occurrence matrix. So once I have the co-occurrence matrix, then we can simply take the representation. Let's say if I have a huge co-occurrence matrix here, let's say we just sorted them, maybe say A and something like that. I might have like A and blah, blah, blah. So maybe we can just take this, the entire column has a representation, right? So I have a co-occurrence matrix, this is big M here. So, and like for each of the column, it will be we will just take it each of the column as a representation essentially. But you see, like that's a problem here because I can have like 100,000 words here and 100,000 words here. Then this representation become like 100,000, right? So then will be quite long, will be quite big, like for any particular application. So what we can do instead, like we can use SVD to decompose that. Like we have M here, we can just decompose to U as V transpose with SVD, right? Let's say. Now then I have if by U as SVD, then I should have something like U here, maybe I write U1 up to uh, UN here S1. So this is like SN, this is diagonal matrix here. And V transpose, let's say V1 up to Vn here. Let's say I have something like this. Now, assuming that my single value here are sorted from descendingly. So this is like the largest one, S1 is largest one, Sn is the smallest one. So this M matrix equal to this guy can be approximated as like I can just truncate somewhere, right? Maybe I don't take all the Sn here. I can truncate up to Sk, let's say, just S1 up to Sk here. So I have like S1 up to Sk. Maybe K is like just about like 1,000, right? And then here I will have V1, still have like, maybe I have V1 tilde up to Vn here, Vn tilde here. But Vn, each of the V here used to be like a n by one vector, right? But now instead like this V tilde here should be just a K times one vector. And similarly, this U will be like U1 tilde and Un tilde. And each of these will be like U1 tilde will be just a 1 by K vector here. Originally, your U1 will be like 1 by N here. So then we just like kind of like shrink the dimension of this U here, right? So then we can take now this U and V will be your representation now, right? Or you can take the average of this as a representation. So does everything make sense? So but that's a disadvantage of this approach, is that like you know that if I have like some new data coming in, my M apparently will be different, right? And then I need to do the SVD again. And think of like this is a you have like 100,000 words in the dictionary. Then your matrix will be like 100,000 by 100,000. So doing SVD on this one is quite expensive. And also like you cannot do it online. For example, you only have one more document, then you need to update the M will be, of course, you expect that this M will be approximately the same as the original M, but either way, you just need to uh, decompose the M like from scratch again. So it's not very efficient that way. Um, so instead, like many tales have this kind of idea combining this window and co-occurrence. So they still have like this co-occurrence. So you can think of like you have this Pij here is the co-occurrence here. So you have updated the Pij. Let's say you have the co-occurrence matrix. Now you have like, some new documents there that you may update a little bit. Now, but instead of like you trying to do decomposition using SVD, so we take an approach more similar to custom machine learning training. So we try to minimize this loss function here. And the loss function is like we have this U and V will kind of make it similar to this Pij here. So we want to make this as close as like actually this log Pij here. And we have this FPIJ is just a scaling factor that is just trying to like scale the co-occurrence. Basically, like we'll minimize this loss uh, as a weighted sum of this uij, uivj, the inner product of uivj and log pij, the square difference of that. But weighted by this log pij, fpij is basically the how likely they will co-occur, like pij. But again, like this co-occurrence here, like we'll kind of like clip it a little bit. So you can either like as before, you can like use upij, maybe like do a 3/4 here to just like make it like more like less. I mean to mitigate the influence for very highly um, or okay to mitigate the influence for like very frequent words, for example an or something like that. Uh, or sometimes like people even like directly just clip it, like instead of like picking something like a 3/4 of that, like maybe they just clip the distribution like somewhere. So so if like your pij is too big, like you have this is like pij here, the concurrence matrix, this fpij here, so will be um simply like this, like clip off. Like so if like your fpij, if your pij is too big, then you just like clip it off basically. So this is like long left glove. um okay, now we have the word vector. Let's say we have the word vector. Let's look at like how we may be able to use that. So there's some very interesting application like for word vector. So the easiest one is like we can take this as some um kind of like a tool to do like calculation. I can call it like calculation in like natural language processing. For example, like if you want to look at like analogies of words. So for example, like if I have like I want to know like what's the correspondence of king for the female king, like what does that what's the word like for female king, let's say. So we can do an analogy or say or something like from man to woman, then what will became to what, something like. So to use that, like we can consider think of like okay, we have like the representation like UK, let's say, right? Representation UK or VK, like let's say we have like representation VK here, VK here, uh, and let's say like if I have VK minus V man plus V woman here. So we want to find what's the corresponding like uh, representation like for the female king. So we can look for that this UI here, that UI that is trying to maximize the inner product of these two. So like UI transpose multiple this thing. So we look at the I here, and this I should give you so R max of that, and this should give you queen something like. So and you can use that to evaluate, right? Because like you know like what's the analogy like you're expecting. You can use that like to evaluate your model and see like okay, does it match your intuition and so on. And another way to evaluate that would be simply like look at the representation there and look at the Euclidean distance and or the inner product like correlation. So you expect that like the word that are more similar may be like more correlated. So maybe uh, for example, like maybe man and boy there like will be more correlated than like man and a car, let's say something like. So and you can look at like the correlation to determine whether your model is like accurate or not. So there's also like some you can have some extrinsic tasks to evaluate this word vector model. For example, like uh, a classic. Okay, this is like an example. Is maybe interesting to look at. Like we just mentioned, like to look at the analogy. For example, you can look at the capital. For example, like for Paris, we know that the the uh, the capital of France is Paris. So we can look at the capital of like Italy is to give you room back. Like, so we can like look at grammar. Let's say like bigger, uh, uh, bigger with respect to big, then cold should be with respect to colder, and so on and so forth. And you can look at like chemistry also. Like you have copper correspond to gold, and then sorry, Cu correspond to copper. Then we want to look at what is correspond to gold. Let's say, yeah, and so on and so forth. Um. Okay, this is just some links here, and we also mentioned like this other extrinsic tasks. For example, you have like limb entity recognitions. This no limb entity meanings that like in the phrase or in the sentence, like what kind of uh, what is the category of this word like belongs to. For example, like we can have like some typical category, maybe like the word belongs to a person or like an organization, a location, or miscellaneous. This gives us an example. Let's say like you have a sentence like this, and then you can identify like what's the um, of course here like we need to have a additional model to do that. Like the Word2Vec do not directly give us this, but assuming that you have um, this two similar representation here, you want to evaluate which one is better, then you may have the representation, and afterward maybe you also train a RNN model, and the RNN model like or like later on we will talk about attention model is going to like spit out like uh, what kind of like category like each of the word belong to. Then we can evaluate the accuracy of this limb entity recognition task here, and to determine which word representation is better. Um, and okay, this is basically all I want to talk about for Word2Vec. Like you can see like how we can get like word vector representation from word. So now as we mentioned, we would like to talk about attention model links, and and we mentioned earlier that like attention model is like now is kind of basically becoming like this um, the default de facto techniques like for natural language processing. And several years ago, like it was still RNN. And compared with RNN, you can see like there's some problem with RNN. For example, like if you remember, like uh, we can of course use RNN for translation. And if you remember like how we do that, like maybe we have a sequence to sequence model. Basically, we have an RNN and we have like one word coming in at a time. Then we have some hidden units, hidden variable like passed to the next time instance. And then we have a next character coming in. For example, this is a car, let's say. Uh, uh, or maybe, yeah. And then like after this one, like it will just spit out a feature or like trying to extract like from this sentence like some feature of that, and potentially from these features here, uh you will okay this start with like some dummy variable like let's say start, then this one will spit out the hidden variable, and then I just plug into back into the model here, and then I plug it back here to get the sentence and to translate the sentence like this here. Now, the problem with like the sequence to sequence model for RNN is that like for a short sentence is doing well, but if you have a very long sentence, then you're trying to extract features from this very long sentence, and actually when you do the translation for the earlier words there, the model may not be able to remember the earlier words. So they kind of like already forget what's going on. Like you have a very long sentence there, you have this feature trying to kind of represent the entire sentence, but like it may not be able to remember the beginning well. So therefore, like it won't translate long sentences as good as short sentences. So I mentioned our engine is more expensive to train uh, um, than, as you will see, like the attention model. So for attention model, like what we're going to do is like let's start with like a kind of like a seminal paper by Banjo. So this is like um, this is like attention models trying to address like some of the issue that I mentioned earlier. But as I mentioned, okay, as we goes on later on, like typically people you heard of like, for example, GPT and so on, like they are all transformers. This is a P transformer models. There's no transformer there here. So it's just an attention model, but it captures many of these idea like of attention model already. So or like the idea of like transformer already. So we have a model like this. So it's also like it can be used for language translation. As you can see, like what we have here is we have like a sentence coming in here. So it have a kind of bidirectional RNN models, and it's going to, so basically you have inputs coming in, so you go like in both direction. Like for example, you consider this direction here, then when you go along this direction, it will spit out some of this like representation, will spit out the hidden variable here. So then you will just collect this hidden variable all together like to this one here, and also like wait a sec. Oh yeah. It's right, but this is not the hidden variable actually. The hidden variable layer, as if you can see, okay, let me just look at here, make sure I have I have to see here okay, yeah. Okay. Now, okay, let my memory come back. So I have to see here. So I have, okay, I have the hidden variables, right? So let's say I have bidirectional case again. Like if I can go this way on this way here. So but either case, I will have like a hidden variable like spit out from the RNN there. So then I can combine. Let me simply combine this two bidirectional RN here, and I just call it the hidden variables, say let's say h1, like for the first one is h1, then it's h2, and so on. Now then I can, let's say when I do the translation and at the decoder side, so I may have like I have another RNN model. So I start with a character, let's say start again. And then like uh for the model here, like I will update the state, right? And the state will update it by uh, the previous word there. So for the first word, I will simply put in the start here, and then like and the state here, like my beginning state maybe just all seal, maybe like just seal there. And also like given the kind of like a character, a what should I say, like a vector representation of the input, see here. But note that this vector representation here will depend on the current words you are decoding. For example, like if I I okay, I always use I cannot uh speak Spanish, I say, right? Then when I translate that, I always need this example because I cannot think of other I don't know other Spanish sentence like no hablo no no puedo hablar español, let's say, right? If I translate like this, so I should get our sentence like this. But note that like the focus here is like if I'm going to do this translation here, so I have this input here. In the conventional RNN sequence to sequence model, I only have like one representation, right? If you remember, like we have like here. So I have one representation to uh, abstract the entire sentence, input sentence there. But for the case of the attention model here, I actually depends on where I am kind of decoding at the moment. I will have different focus of the on the parts of the sentence of the input sentence. So for example, like uh, maybe I put also lojo abo. So then for example like let's say like I'm decoding Puedo, then like my focus will be like on cannot here, right? Or like maybe if I habla, so if I'm kind of like decoding habla, my focus would be on speak here, something like. So how can I do that? It's like my CT here will depends on like where we are decoding at the moment. And so you look at the CT, what is CT? CT is basically weighted sum of the hidden variable here, hidden variables here. But it's weighted by this alpha here will be some kind of a match. I would call it like some kind of like match filter, like because I'm an engineer. So it's like alignment score of like how this guy how the current input or current state is here align with the hidden variables. For example, like at this moment here is like habla, and as I have speak here. And if you look at the hidden variable here, so if you train the model well, supposedly this one should have a high correlation with this guy here. So therefore you should have this ETJ for habla and speak should be big, and for the west here would be kind of small. So therefore, like I have like a cannot here, like I have I here, Spanish here, let's say. So I should have like alpha T3 here is big, for the west will be small. So therefore, like I will have this CT here, it will be focusing on this speak here. So is that clear what we have here? So this is the attention model. So now for the transformer, it's quite similar. So we have basically the attention model is very similar. So um, we have this alignment score earlier. Is that you make it more quite generic here. But for transformer, typically we'll make it quite concrete, like how do we do the alignment score? And we'll split it in the three ways. Basically, like we have three components here. We have a query, and key, and value. So actually, this is very similar. If you, I don't think you guys will remember, but for Hinton's model, like when we talk about our NN there, we talk about there's a factor model that is more elaborate than just like plain our NN. The factor model is very much like similar to this one. Actually, like almost identical to this one. So you can think of like each of this is like a factor there. So we have a different factors, and you have a a almost like a a dictionary with different keys here. So I have like I have key for diff- different words here. So for example, I have key for a, key for the, something like that. And then I have the corresponding value to represent like what is the good representation for a and the and something like that. Right. So given a query there, like then I have a query. The query may be a word like maybe man, something like that. And then maybe like you have like for this dictionary, you have like, of course you have a man here, but maybe you also have a boy here. So value for maybe maybe it's better write like that. When v man, v boy, right? And this is a k k man, k boy here. So if you have the good word-to-web representation, you should have your this query, this q man here should have a high inner product with like this k man here and k boy here. Probably like high, very high with k man here, and also quite high with k boy here, right? And then like basically like when you have this query, uh, do an inner product with like each of the keys here, you will do a softmax to normalize into a probability, right? And then you will use the probability as a way to weight the sum the values here. So for example, if my Q is a man here, Q man here, then most likely my output will be like very much like V man, but also maybe like with some relevant, maybe V boy here, maybe this is a zero point 0.9, this is a point, I don't know, maybe 0.9 is a kind of like 0.5, maybe this is a point 2, and then I have say some other uh, non-zero weights here, like add together. Um, and yeah, and that's basically like the core of the attention. Um, then if you look at the transformer, so what it okay uh, and actually it's actually always better for me to. It's too late to do that, but I should use a finer pen here. And I have, I'm also here, you see like I have this multi-add attention. What it does is like, I don't have like just one attention model here. I can have multiple attention models here. So you can think of like, because I for each of word here, like it may have like different from different contexts, it could have different meaning here, right? So you can think of like lots of word have like lots of different meanings, right? For example, bank here, it can like mean lots of stuff. Like can financially, or it can be territorial, like on geometry and not geometry, geography. Um, and so depends on different contexts, and I probably need to have a different model for that. So then I can have a multi-head for that. It's like essentially like you have um yeah, actually like just for each different context that you can have a separate model. Um, then uh, then the transformer essentially like will be like this. We have what it goes to okay okay, let me to start with first. This original transformer, the goal again is like doing like language translation. You can do language translation for that. So let's say you have come in like a sentence, or again, I have like, I cannot speak Spanish here. I come in a sentence here. So how it works is that it's going to try to, uh, similar to our end, it will spit out like one sentence at a time. So not one word at a time. So it should like output like two, and also like it will output essentially like not the word itself, but actually like for our end also like, I didn't emphasize, but it's usually it will output like the distribution of all the words, and then from the distribution you're going to like sample that, like for example like you, after you're going through the entire model, you'll get a distribution of like all the words, say all the Spanish word here, and I have like a high probability of draw here, and then when we sample it first, maybe actually I should sample no first, but anyway, sample no first, like for the first character, first word there, um, uh, and afterward, so similar to our NN, this will pop back into this model here, and then you generate the other words. So, okay, how does it work in detail? So we know a portion of this already, right? We know the attention part, and we know the embedding parts, right? We have some embedding that's basically word to word, right? We discussed earlier. So for all the words that coming in, it will just say do a word embedding. So each of the word here will become like a vector typical length of like 124 here. So let's skip this skip this positional encoding component first. So this is essentially like, is actually I can jump ahead to talk about that anyway. So this is just a, because I for the attention model, um, if you think of that like in the attention model like here, if you look at the context, for a word like, let's say I'm trying to decode at this moment, it basically just simply attend to all the hidden variables, right? They will be considering each of the hidden variables like in the original sentence, in the equal manner. So like you will consider like each of them equally. So in the sense that you just dump away the, position or the all the information here, right? So I I don't care whether your input is that I cannot speak Spanish, or like, of course like the our NN here supposedly is take care of that, but actually like in this model here like it doesn't use RNN. What I should say is that in this model here, if you don't use RNN, for example, if I don't use RNN here, then there will be no positional information at all. So for example, like if I simply have the word embedding coming in for each of the word here, there will be no positional information. I will take every word here like, um, in the same token, in the same manner. So therefore, we want to add back some kind of like position information here. So this positional encoding is simply generate some kind of code you can think of. Typically, it's like just, um, some sinusoidal, signal here. So you can think of like this is a 1024 lane 1024 vector here. So you can do it a different ways. Like I just give an example. Let's say I can do a sinusoidal in signal here. Like for example, like for the first, word, maybe I will just modulate by this guy. And the second word will be with this guy here. And the third word will be this guy here, let's say, and so on and so forth. And I will simply add this modulation into my original word embedding there. So then there will be some kind of, positioning information in the embedding now. Then afterward, then we have this attention, right? So the attention will be like a self attention. So I will take the key. Earlier we have the key value and also the query, right? Here I will take the key value and, key query and the value, all the same thing, as the modulated embedding here, so of the word here. So basically keyword value and embedding, all of them are the same. So and then in the sense that I will have something like basically have a modulated sentence, uh, modulated word representation of the sentence, modulated by the positional code there. I have like I cannot, something like that, whatever, some words here. And I have like also here, I cannot, something here. Now I go through this attention model. So you're doing a self-attention. Like for this word here, you're trying to attend to all of these guys here, right? So if let's say like if I have actually maybe okay. Yeah, that's right. I cannot speak, let's say, Spanish or something like that. So it's going to, in this case, I would say like this simple example, like it may not be uh, uh, very obvious like why this will help, because I have this I, it looks like it will should always attend to this I here, right? Uh, but if you have a more complex sentence, so let's say uh, I cannot speak Spanish because uh, my ear are bad, whatever, let's say. So then if you have more complex sentence, then maybe my I here will attend to like not just this I here. Maybe I will attend to the my here, right? That will be get some attention here. It won't be like something like a trivial case that like I will always like my word always attend to myself. I may have like also attend to some of this relevant information. Um, for example, I cannot, let's say, uh, I don't know, speak, may attend to speak. Maybe years is interesting also. Like when we speak, maybe it will try to attend to the word years as the and so on and so forth. So and okay, after this attention, self-attention, then you we have we have okay, after the self-attention here. Hmm. So we have the output. We'll simply go for like some other feed-forward layers here, and then we will just repeat it like several times here. Basically, we have this layer. Okay, here we'll repeat like n times, I say. So this will repeat n times, and then afterward you have this output like similar to the our to the sequence to sequence model, like in that sequence model case. We also have like only one representation here, but then this representation will potentially will be have hopefully will be a better representation. Oh, plug into this one here, and again, like, if you look at the this okay, by the way, this side we call it the encoder here, trying to encode this sentence, original input sentence, and this decoder here is doing very similar things. If you can see here, it first of all it is self-attention here with the output sentence here. So of course the output sentence is like going one word at a time. For example, like you have like yo no puedo and so on. So you will spit out like yo first or like or no first. Yo no, or I don't know. It doesn't matter. So and then like once you have this, you will plug into this one here. For example, like you have a partial sentence like yo no hablo puedo, right? And then you try to predict the next word here. So you have YOLO, puedo, like kind of like plug into here the 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 input here, And then I again go for positional encoding. I'm go for this entire thing. I'm eventually okay. I guess I am over time, so I will just stop here. Maybe I'll repeat a little bit the attention model next time. And so if okay, so I will see you guys Thursday then.